Good morning, everyone. Let's start this morning. So far in this class, we've been talking about some components of this more interesting definition of structural engineering. And last day, we talked a little bit about how we can put some of the shapes that we talked about on Friday last week together to make a structural system that's capable of supporting gravity loads on the floors. Concepts of tributary width for joists, tributary area for girders and columns, and we had time to do a brief example on how we got the loads on the joists and the loads on the girders. And then in the lab the other day, we reminded ourselves how to do those statics problems so we could get shear and moment in arms, for example. And when we come to flexural members later on in the course, we'll use the shear and moment to figure out how big, like what W shape are we going to be using to work as that joist or as that girder. So we talked a bit about gravity framing. We're going to continue to talk about these shapes we can't really analyze. And what I mean by shapes we can't really analyze, we talked about cross-sectional shapes, and in lab on Monday we talked about normal stresses, shear stresses. We have some mechanical tools that we can use to try and figure out what the stresses might be on the cross-section. We also know there's some inherent variability as to whether or not we can do that accurately, right? So we talked about the inherent variability in the resistance. I talked in lab the other day about, well, we've got a member that we think can probably carry 675 kilonewtons. It needs to carry 849. Maybe it can, rarely, right? We think it's 675, but there's a very, very unlikely possibility that it could be strong enough to carry 849 kilonewtons. Today, what we're going to continue talking about is the forms of structures and how we need to apply some simple tools and some basic statics to try to analyze what the forces on some of these members might be, and not even the forces on the members really, but we're trying to figure out where the loads come from and how they get to the different kinds of structures that we're used to analyzing. So today we're going to talk about bracing and braced frames. Okay, so gravity framing keeps the building up, keeps the loads up from falling downward. Bracing in structures and the braced frames in steel buildings, they have a similar role. They're responsible for keeping the buildings upright, but they're primarily responsible for resisting loads that come at it sideways, right? Horizontal forces. Can you think of any kinds of loads that might make the building try to move sideways that this bracing might be responsible for resisting? Any kinds of loads you can think of? Wind, right? You've been in a windstorm before. In a really strong wind, you can get blown backwards, right? So wind is always acting. It's faster, it's slower. We'll talk about wind loads in lecture 7. But wind is one thing that can impose lateral force on structures. Anyone think of anything else? Earthquake. Earthquake's great because earthquake loads, they come, the ground shakes back and forth. That imposes an acceleration horizontally on the floors in our structures. We'll talk about earthquake loads in lecture 8. Very simply, everything, wind and earthquake are very complicated, but we'll dumb them down as much as we can for this course. Wind and earthquakes are the two primary sources of lateral forces on structures. The braces, we'll see, are primarily responsible for resisting those loads, and we're also going to see that although gravity loads act predominantly downwards, there is still an action that we treat as coming sideways from these gravity loads to deal with some imperfections in our structure, and we'll talk about that in lecture 9. Today what we're talking about is what bracing looks like, how to identify brace frames in steel buildings, and to show some examples of bracing in these structures. Okay, so this is the Justice Building when it was pretty much done. There's still a little bit of steel deck on the roof that needed to be installed, but this was 99% complete in terms of the steel contract work. We can see here we've got some bracing throughout a couple of the bays. A bay is basically the space between two columns. So this is a bay. Okay. In this case, we can see basically the bracing going between the corners of all these bays, between floors, between beams and columns, connected by these gusset plates. Basically, we've got members coming down between some bays on this side and members coming down between some bays on this side. And when we have forces from wind perhaps blowing on our structure or pulling on the structure due to the suction forces on the other side, basically what we're going to focus on today is how to trace these loads in through the floor and the wall systems, and how we can figure out how they're going to be acting on these bracing systems so we can figure out what the brace forces are going to be. This is a slightly simpler structure. In lab the other day, we did a very brief example of a truss system that had some flat bar bracing. You can see this is, maybe you can't tell from this view, but these are flat bar braces, just rectangular bar stock that is connected to the gusset plates. This is a different kind of bracing system. It's similar, right? Obviously it's diagonal, but in this case, we've got two bracing points coming down and actually meeting in the middle of a beam within the same bay, right? So that's one bay wide. So here we've got both braces in the same bay. They come down and meet to the same point here. And the other thing that's interesting about this bracing, as we talked about a little bit, or as I alluded to in lab on Monday, these kinds of braces are not very good at taking compression forces, right? The resistance to elastic buckling of that flat bar in lab the other day was like 2 kilonewtons. 2 kilonewtons is not a lot of kilonewtons. But in tension, it could carry 675. And so what we're going to see when we're looking at bracing like this is called tension-only bracing. We're going to rely, in this case, only on the tension members to resist the lateral forces coming through our structure, and we'll talk about how to do that. This is one other kind of bracing. It's very similar. Actually, it's kind of like a combination of what we saw in the school on the previous slide and what we saw in the Justice Building. They're bracing in separate bays, but they both come down to meet at a central point that's not carrying any gravity load here. Does anyone know where this building is? Grand Harvey, that's exactly right. If you play hockey or if you go up and do whatever, I don't know what else you can do in here, but hockey players will recognize this atrium space. This is at the Grant Harvey Arena. Here we've got HSS bracing with a different kind of connection to the gusset plates here. So we can see in this image, we've got HSS that are quite sizable with big gusset plates. Here we've got flat bar stock used as tension-only bracing. And here we've got HSS members. In this case, they would be tension and compression bracing. Okay, so HSS are very commonly used for bracing members. They look nice, especially when they're exposed architecturally like you've seen here. Flat bar bracing is kind of ugly, hence why they're burying it within this masonry wall for this structure. Okay, so after this, you should be able to identify and describe braces and braced frames and steel framing and how they can be arranged to carry loads down to the foundation. You should be able to calculate the loads acting at each level on a braced frame and draw those lateral loads on a free body diagram of a truss that represents the braced frame. And finally, but a little bit less important, well, the last part here is important, but you should be able to differentiate between determinate and statically indeterminate bracing. You should already be able to do that if you're okay in CE 2033. You talked about statically determinate structures in statics, statically indeterminate structures in structural analysis. We're not really going to do much with indeterminate bracing here, but you should be able to identify when you have statically determinate or indeterminate bracing arrangements. And finally, you should be able to differentiate between tension compression bracing and tension-only bracing. Okay, does anyone have any questions about any of the context that I've shared so far or any of these three learning objectives and what they might mean before we get into the material this morning? All right. Before we do that, I'm going to have a poll everywhere question here in a minute, but I'll keep the slide up for a second. I want to just make sure that some of the stuff we talked about in lab on Monday stuck with most of you. We're going to be doing a lot of problems similar to this one. And so I just want to see before we get into this, if you're capable of doing a problem like this, what I want you to do is take a couple minutes, maybe it should really take you a minute. I want you to figure out the axial force in the bottom brace for the truss that's shown here. Right? It's a vertical truss, it's pinned at the bottom, it's got some point loads acting on the joints, and I want you to calculate the force in this member here. Okay, I haven't given you much information here, but we'll just call this a 3, 4, 5 geometry for that bottom brace. Take a minute, try and figure out what that axial force is in that bottom brace, and I'm going to see if I can't maybe activate the Poll Everywhere session online so that you can go in and answer the question after you get a response. Feel free to talk about this with your friends, your partners, the people next to you. If someone's not here you want to call, feel free to call your friend. I don't want to hear my thoughts really for the next minute or so. Okay, so it is actually active. My thoughts are scaring me, people. I want to hear a little bit more discussion in the classroom. Talk to people next to you. Don't feel pressured, but don't leave me alone here with my thoughts. I'm just going to shift to the next slide here to see where we might be sitting. Again, I don't know how I tried to change this one so that we could see the number of people who have responded. For all I know, 100% is one person. Put your hand up if you've answered. One person. Okay, so it was one, or maybe two. Great. Take maybe 30 more seconds. We'll come back and talk about it. A little hint, if you don't have a calculator and you think, oh, geez, I can't do this problem, I don't have a calculator, you should be able, from these 4 answers, to pick something reasonable. Okay. So we've got a 460 something kilonewton force in compression. We've got 370 kilonewtons in compression. We've got 463 kilonewtons in tension, 370 kilonewtons also in tension. Okay, so the same couple numbers, tension or compression, should be able to, at least from those answers available, pick something that makes sense. Okay, well, people are either sitting there bored or maybe not talking about the problem at all, so that's fine. What's the answer? Anyone want to share? Anyone feeling comfortable to discuss what you submitted on the poll everywhere? Or if you didn't and you still think you have the right answer, what it is and how you got it. First of all, is the brace in tension or is the brace in compression, do you think, that bottom diagonal member? Tension, hands up. Compression, hands up. This is in tension, okay? Now, how would we figure that out? Well, we'd actually figure it out more or less the same way as we would figure it out if we were trying to calculate that force. One of the things we might do here is we would draw a section cut through the bottom 3 members, do some kind of method of sections, and if we do that, we know that these 2 vertical bars, they're not going to have any horizontal component of force. All the force acting on that section of the truss is to the right. That means the force in this bar needs to have a component of force to the left, which means it's down and to the left, which means ultimately that brace is going to be in tension, right? So we know that brace is going to be in tension. I'm going to have something like this for the other member forces. So it's in tension. So that gets rid of half the answers that we had on the slide there. How would we figure out what component of force that brace needs to resist and ultimately what that tension force would be? Some of the forces in X direction, right? We did this on Monday, except vertically, so why? But here, if we did some of the forces in the X direction, some of the forces in X, maybe calling to the right positive, that's 0. We have the X component of the brace force, or this bar force to the left. That's going to be whatever that tension force is. I'm just going to call this T. That's going to be T multiplied by 4 over 5, right, based on the geometry of that triangle. And that has to resist the 50 kilonewtons plus the 100 kilonewtons times 2, plus the 120 kilonewtons. So automatically, once you sum up these numbers, 50 plus 100 plus 100 times 2, that's going to give you a total here of 370 kilonewtons to the right. And so, you know, I may have been slightly tempted to say, well, the force is 370. Is the force 370 in that brace? No, that's the horizontal component of that force, right? So we've got the horizontal component of that force is equal to 370, which means T is 5 over 4 times 370, which would give us 463 kilonewtons. Right, so just practicing again that method of sections. When we've got vertical members, it's very easy to apply equilibrium in the x direction to figure out how big that force is going to be. And you're going to be doing that lots of times on your assignment, and so it's important that you're able to do that. Does anyone have any questions or concerns about that problem before we continue on? Okay. So that's a simple truss problem. And you might be wondering, why are we doing a simple truss problem? Well, I gave you a little bit of context for that on the first day. What we're going to spend some time doing is identifying the bracing and brace frame regions in a steel structure. And we're going to talk about how we often idealize those braced frame systems as simple trusses for the purpose of performing a structural analysis to get the member forces. Okay, so this was the example structure that I showed in lecture 3 the other day. This is the one we built up from the foundations to the top of the steel deck. And it's the building that we're going to be working with pretty much every lecture, or at least on the lecture where we're talking about applying these concepts for the rest of the term. So the other day we talked about floor plan drawings. Today I'm going to talk about elevation drawings and what elevations are going to be intending to show you. And what I'm going to show you is how we're going to represent the bracing arrangement on this face here, right? You can see there are some diagonals between beams and columns on that side. There are some diagonals between beams and columns on this side. And if we wanted to communicate the information to the fabricator of record and the general contractor about how that's going to be arranged, we would draw that in 2 dimensions, something like this. What we're going to identify in this drawing, we've got several different pieces of information. First, we're going to identify where the bottom of the column base plate is. That's basically the elevation where the steel structure starts, just above the foundation. Sometimes that'll be just a reference elevation of 0, but sometimes it's an actual elevation above sea level or something like that, depending on how the contractor wants to work through the contract. And then we're going to identify where the height or the top of steel is for all of the floor elevations. So here we've got 1, 2, 3, 4 floors above the base. The top of the steel members, which is just at the underside of the steel deck, might be at 4.5 meters, 8 meters, 12.5 meters, 16.5 meters. And what that means is we've got a floor elevation of 4.5, a story height of 4, story height of 4, and a story height of 4. What's important today is that we're going to identify where the bracing is here. And if we look at the members that are forming the space around the bracing, we've got some beams and columns that are sort of getting closed in or that are closing in the bracing arrangement. The bracing is what's highlighted in green here, where once we do our structural analysis, we're going to provide the factored force that we use, whether it's in tension or compression. And the reason for that is just like the joists and girders, we don't design the connections usually as the engineer of record for these kinds of elements. That's the contractor's responsibility. Oftentimes, the connections are where the contractor will start to be a little bit more competitive economically. They know how they like to build certain things. Some people like to bolt things. Some people like to weld things. Some people have pre-set up systems for making certain connections. And so they like to have those details on their own so that they can price these projects competitively. But we are going to give them that axial force that comes from the structural analysis. I probably shouldn't have 6x6 here. I've got basically saying this is an HSS 6x6 of some kind. I should have said 152 by 152, but we're going to tell the contractor what the braces are that we picked, and we're going to talk about how we picked those members in the next couple weeks. So overall, the braced frame that we're going to be looking at is whatever the bracing touches. So the bracing comes down to connect to this column, up to connect to this beam in this column, and so on and so forth. And the braced frame system that we're going to be working with in this elevation are all the bold black lines with the bold green lines. If we come back to the floor plan briefly, we're going to see that in some cases, we're going to be locating, and I've got some, just ignore these scribbles here. Basically, in plan view, we're going to communicate where the bracing is, and that's often by having some kind of dark dashed line. Sometimes it's a dashed box around the bays where we have the bracing. This is going to tell us in plan view where the braced frames are so that we can make sure that we're designing all the other elements accordingly when we have the bracing connected to those elements. Okay, so basically the way you identify the braced frame is everything that the bracing touches is going to be part of the braced frame arrangement, and we're going to be working with those members to simplify our structural analysis. Does anyone have any questions about that before we get going with the rest of the material? So that's one thing. We've got these braces, and we had in this problem a very similar looking truss, right? This is basically, without the geometry being quite right, this is more or less that braced frame system that we see here in elevation. We have point loads in our trusses, right? And in statics and in structural analysis, you're basically given these point loads, and you said, look, there's these point loads on these truss, figure out the member forces. Where do these point loads come from? How did they get there? That's what we're going to be talking about for the next little bit. How do these point loads actually get to these trusses so that we can perform this structural analysis? All right, so what I mean by that is we're going to be talking about the load path. How does the load get from under wind? Maybe there's wind pushing this wall in. How does the load get from wind on wall on floor to braced frame? And how do we get those point loads acting on the braced frame system so that we can analyze them and perform our structural analysis to figure out how strong these elements need to be? There's a lot packed up into this image that I'm going to show you here. Basically, what this is it's trying to communicate where the pressure from wind, for example, might be. And basically, the easiest thing to do here is to think of the wall system as if it's a floor system in our regular gravity framing. Okay, so we're going to treat, more often than not, we're going to treat wind as a uniform pressure in this course. I'll talk about earthquake loads and the load path for those later on, but it's much more simple. Wind basically pushes on the wall the same way a uniform load would push down on the floor system. Okay, and what that means is the floor is supported by, the wall is supported along the top edge of the wall. Usually there's either some kind of like glass glazing system, or maybe there are some steel studs, like cold form steel studs that form a wall system. Basically, this wall is going to bend in plane, and then along the top edge and bottom edge of the walls, the floor system is going to support that wall and the pressure on the wall as if they were acting like joists. Okay, so here, take this building and turn it on its side. Pretend it's a cantilever gravity framing system. And what you have is pressure on the wall, which acts like the floor. We've got uniformly distributed loads that go to the floor levels, just like the uniformly distributed loads that go to our joists. And then the trusses, or the brace frames, more or less act like girders. Okay, so the uniformly distributed load is going to push on this floor. We're basically going to treat this great big rectangular floor as if it's just a little beam. Okay, and what I mean by that is we're going to take this floor and we're going to say, okay, let's treat it as if it's a beam that looks something like this. We've got a pin and a roller, and it's got a uniformly distributed load on it. And that uniformly distributed load comes from the uniform pressure multiplied by whatever the width tributary to those floors might be. Okay, so here we're talking about a tributary width for each individual floor level, and we do the same thing that we did for joists. We have the center line dimensions on either side of the floor. So here we have half of this height plus half of this height gives us our tributary width. So again, we can say here that the distributed load on this beam would be the pressure from whatever this might be, the wind, multiplied by the tributary width for the given floor level. What's keeping that floor there? We've got a uniformly distributed load acting on that floor. It's not accelerating into space at an indefinite amount. It's staying there. What's preventing that floor from just getting pushed off by that uniformly distributed load? It's there anyway. What keeps the joist in place? What supports the joist that's carrying uniformly distributed load? The girder, right? The girder supports the joist. And like I said here, the braced frames are essentially acting like girders. Basically, there's going to be a connection between the floor system and the beams that are coming into the braced frame. And oftentimes how that looks, I'm showing it kind of simply here, but oftentimes there's some means of connection between the concrete floor and the beam within the braced frame, and that load's going to be more or less distributed along the width of that beam. But we're going to connect the floor system so that when there's a horizontal force on that floor, the horizontal force gets transferred into the beam of the braced frame, and the reaction provided by that braced frame to keep the floor in place is going to be the action of the floor pushing on the braced frame. Okay, so basically what we have here is we've got reaction of the floor system, and those reactions are going to be the point loads acting, and we're going to assume more or less at the joints or at the elevations of the floors acting on the braced frames. Okay, so just like the load goes through the floor down to the joists, into the girders, and into the columns, these loads go through the wall, into the floors, into the braced frames, and ultimately they get transferred down to the ground at the base of the braced frame through a combination of shear and axial force and compression force so that the building can stand up and not topple over. Okay. Are there any questions about the concept shown here in terms of tributary width? This is the second time we've seen that in lecture. And the analogy that I'm making, or the analog between how the loads go through gravity framing, as we talked about on Monday, and how these loads might go through the floor system to the braced frame system in lecture today. So we're going to have some time to practice that. I guess I'm going to reiterate what I just said here. We've got basically a uniform load that's acting as basically distributed along the floor member itself. We're going to idealize this floor as if it's got a simple beam with a pin and a roller at the location of the brace frames. Okay, that's an important point. If they're not at the location of the brace frames, then you're not actually going to get the right answer. And what I mean by that is if instead your brace frames were inside, they're not always on the outside face. In that case, I would draw this as having a pin and a roller, something like this, and it would have a simple span and some cantilevered spans, and the statics of that problem would change ever so slightly. Okay? In this case, I guess the forces here and here would be more or less the same, but the load isn't always going to be uniformly distributed over the length of the beam or the floor, and we'll talk about that in a second. Basically, we've got one of these beams at every single floor, as I showed on the previous slide, I guess. So we've got one of those beams at each floor level. That means we have 4 beams. And we're going to use the statics of the floor system, just like we would for a joist. These loads are A for the floor and are B for the floor. If we're looking at this braced frame, we're going to analyze it just as a simple truss, which means we're going to take all the members that are in the braced frame. We're going to assume that they're connected by frictionless pins so that we can do our method of joints or method of sections. And these floor reactions that we're taking from our statics here, that's going to end up being the actions on our braced frame system. Okay, so the only thing that's new here is the load on the floor flowing through the floor system, and then the reactions for that floor acting on the braced frame. All of a sudden, we're back to where we would have been comfortable with, I say comfortable maybe loosely, in 1023. Okay. Does anyone have any questions about this concept before we continue on? Now, I know that you can do this problem because you just did it for me. Right? The new stuff here is figuring out how those point loads get there and how to calculate them, and that depends on the load that we've got. Now, so we've gotten to the point now where we can figure out, okay, there's wind or a pressure on the building. How do we figure out how much of that force goes to the brace frames? Because ultimately, the brace frame needs to be strong enough to prevent the wind from toppling the building over. We've got these loads, and now we have to do the structural analysis. And the structural analysis is something that you've done before. You can get the axial force of the members from method of joints or method of sections, and we practice that on Monday. In this course, you don't need to do anything fancy other than method of joints and method of sections, But we're going to start to use structural analysis software, STAAD.Pro, and in lab, not next week, because I want to do something more fun next week, but the week after, we're going to start tinkering around with STAAD.Pro to see how we can draw some structures and apply loads to the structures. But in the course, we're going to start practicing using a structural analysis software to do the same problem. As long as you model the problem the same way as you model it for doing the analysis by hand, you should always get the same result. And so we're going to start with these very simple structures that you know how to get the answer for by hand using method of joints or method of sections. And we're going to see if we can get the same answer using STAAD.Pro. Okay, so you might use method of sections, you might use method of joints, you might use STAAD.Pro. What I want to talk about a little bit is differentiating between indeterminate structures and determinate structures and different types of bracing arrangements. Okay, this is what's called a zigzag bracing arrangement. The name's probably pretty obvious. It kind of zigzags back and forth between the joints of the truss. But there are many other kinds of bracing arrangements, and these bracing arrangements may or may not actually be statically determinate. You learned how to do the analysis of statically indeterminate trusses in CE 2033. I would say 0% of structural engineers use the force method or virtual work or Castigliano's theorem to solve the forces in a statically indeterminate truss. I would say 10 to 15% might use something called an approximate method. Do you talk about approximate methods of structural analysis in 2033? I feel like you don't anymore. It used to be covered. I'll talk about that very briefly today. But in 2033, you basically said, okay, well, if I have a statically determinate truss, I can do method of sections or method of joints. If I don't, I need to do something more rigorous. So zigzag would be an example of something that's statically determinate. And that kind of makes sense because we've already solved similar systems using method of joints and method of sections. That means we can just use equilibrium to solve the problem. You can do method of sections. You've got three member forces and three unknown member forces and three equations of equilibrium. And if we do it from a method of joints perspective, every time we come to a joint, we have two equations of equilibrium. So that means here we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 joints to work with. And every member force is an unknown, right? So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And then we've got the unknown reactions as well. So we've got 16 unknown member forces, 4 unknown reactions. We've got 10 joints, which means we have 20 equations of equilibrium. The equations that we have is equal to the number of unknowns we have. That means we can use equilibrium exclusively to determine what the forces are. That by definition means that it's statically determinate because we can just use statics to figure out what the member forces are. Another arrangement here is called chevron. I don't know why it's called chevron, but basically you can either have a V kind of shape or you can have an A kind of shape. In fact, I think this is called inverted chevron because I think chevron is more of a V shape. But it looks kind of weird because you might say, but Taylor, if I do method of sections here, I'm going to be cutting through 1, 2, 3, 4 members. That's 4 unknowns. Can I solve those 4 unknowns using the equations of equilibrium that I've got for that section? I've got 3, right, equations of equilibrium. Can I figure out what those 4 member forces are with that section cut? Yes, no, maybe so. I can't, right? I've got 4 unknowns and 3 equations. That means I can get all of them in terms of another force, but I need something else. Usually that would be compatibility or some kind of flexibility considerations. But if you look at the number of joints here, because these members are all connected at the center of these beams, we're actually introducing 1, 2, 3, 4 new joints, which means we're introducing 8 new equations of equilibrium, and we're only introducing 4 new members. And so if we are, that's not technically right, I guess we've got a few more members than that. So if we're looking at this, we've got 1, 2, 3, 4, 5, 6, 7, 8 new members and a few new joints, 4 new joints. That means we're adding 8 new equations and 8 new members. So technically, it's statically determinate. And there are some interesting ways that you can cut through this truss to make it statically determinate and figure out what those member forces should be. but my goal here is not to go through that. It's just to identify that this particular bracing arrangement is statically determinate, and you can figure it out without doing anything particularly fancy. Now, if we think about what was in that school, or even similar to the Justice Building, this is called two-story X bracing because it makes an X over 2 stories. We're not very original as engineers, right? It's two-story X because the X is over 2 stories. What's different between the two-story X arrangement and the chevron arrangement? Like, you got the same number of braces. It should be easy enough to solve, shouldn't it? So what's going on here? Well, it's technically statically indeterminate, and I don't quite think now that I'm looking at this that the member number is quite right because we've got 1, 2 less, so 22 members. But if we look at the number of joints and the number of reactions and the number of members, I think it's actually, so R should be 4, M should be 22, so we've got 26 unknowns that we don't have. That should be, whoops, that should be 22. But we only have 24 equations of equilibrium, which means that this two-story X arrangement, as we've shown here, is statically indeterminate to the second degree. We need 2 more equations that we don't have to figure out what the member forces are. And that means you might need to do force method, but ultimately in this course, it means we're going to use the structural analysis software. Another common arrangement is X bracing, right? So X between the stories. And this is more indeterminate because we actually lose a couple joints here, and we actually lose a couple members as well. So I need to update this number of members here. But this should be 22. It still ends up being statically indeterminate because we have 20. That should be 20. We've got 24 unknowns, and we only have 20 equations to solve them. So this is statically indeterminate to the 4th degree here. This is to the 2nd degree. And again, that means we're basically going to be using a structural analysis software to figure out what those forces should be. Now, I already said you don't have to know 2033 stuff to be successful in this course. Structural analysis software in some ways is based on some of the principles from 2033. There is another way that we can estimate what the forces in these members might be. Okay, and I'm going to talk about this on the next slide, perhaps. And I'm going to focus on these 2 systems here. Okay, so we're going to look at X bracing, which uses tension compression bracing, and an X bracing system that might use a tension only system. If I had a X bracing system here, let's just say we've got the X bracing system, and I want to try and figure out what the forces in those members might be, is there anything that I can do to simplify the problem? Like if I make a certain kind of assumption, perhaps. Can I solve that problem if I make an assumption about how that system is going to work, instead of having to do like a really fancy structural analysis? Any ideas? So I already said X bracing here is statically indeterminate to the 4th degree because we have like 1, 2, 3, 4 additional members that we don't have in zigzag and no additional joints. Is there anything I can do with these members to try and, it's not going to be exactly right, but approximate what the forces in those members might be? So let's look here. If I was to draw a section through that truss, I'm going to have a member in tension, a member in compression, and I'll ignore the columns for now. Is there any reason to think that the force in this member is going to be significantly different from the force in this member? They're the same length, they're the same section size. Wouldn't they be somewhat similar? Might not be exactly the same. Whenever we have X bracing and the arrangement of the bracing is relatively similar, one of the things that we can do to approximate or do an approximate structural analysis is that we can assume here, and technically the answer is to assume that the X component of the tension brace is equal to the X component of the compression brace. But if we have the same geometry for both braces, we're going to assume that the tension force is equal to the compression force. Okay? As long as the brace is being designed to take compression as well as tension. We can assume that they're going to be close enough that we can approximate the tension and compression forces by assuming they're the same. And if we do that at each level, T equals C, T equals C, T equals C, not 0, but C, that's a new equation, that's a new equation, that's a new equation, and that's a new equation. We just introduced 4 new equations by making an assumption about how the system works to figure out what the force in these members might be. Okay, so by assuming T is equal to C, we have those 4 new equations, and then we can use statics from there to figure out what the force might be. Sometimes we're going to be using X bracing that's quite slender. Maybe it's a flat bar brace, right? We saw the other day. If we try to design this brace to take any compression and we decide to use a flat bar brace, we're going to say, well, we can get 2 kilonewtons of force out of that brace. That's not very much. It's going to buckle at a pretty low load. And the other member in tension, we saw the other day in our case here, we had like 675 kilonewtons for that 15 by 150 bar. We call this tension-only bracing because only the tension member is effective at resisting any of the forces. That little compression member is going to take its 2 kilonewtons and it's going to buckle. Not going to help carry any additional load. That doesn't mean it's failed. And in lab next week, we'll play with some, I don't want to say toys, but that's kind of what it is, but little structural models, and we'll mess around with tension-only bracing system to see when you push on the structure what happens, and you'll see the tension member get tight and the compression member buckle out of the way and be useless. It's statically indeterminate here because we still have 4 additional members. So we have 4 equations that we don't have to solve this problem. What can we do to figure out what the tension should be? What we can do is, again, make an assumption. And the assumption is going to be that because these elements are going to buckle at essentially 0 load, we're just going to say, well, the force in this brace is going to be 0. It can't carry any load. It's just not effective. It's going to buckle and it's going to go away. And what that means is we can treat the system as if only the tension members are there. And all of a sudden, we've got a statically determinate system again. Okay, so the equation we're introducing here is that C is equal to 0. Those are 4 new equations. And now we can use the remaining equations with the remaining unknown member forces here to figure out what those tension forces can be, so we can figure out how big those braces need to be. Okay, does anyone have any questions about statically determinate versus indeterminate systems, what it means to do an approximate structural analysis for X bracing if you've got tension compression bracing, or what it means to do an approximate analysis for tension only bracing, and what these equations are that we're introducing for each of those members? Right, that's an important concept. Tension compression bracing, we assume that the forces are equal. Those are new equations we can use. Here we assume that the compression brace force is 0. That's 4 new equations we can use, and that simplifies the problem so that we can solve it by hand. Are there any questions about those concepts before we move on? Okay. The last thing I'm going to talk about briefly is where the brace frames should be. If the structural engineer had the choice over everything, they don't, by the way. The architect's going to tell you to put everything in just the worst place that you could think of, right? Because they want to make things beautiful, and you just need to make sure it can stand up. But if the engineer was also the architect, he would put all the braced frames on the outside, because from time to time, we'll get some non-uniform load acting on the wall. We'll talk about how that could arise from wind load, for example. And if the brace frames are on the outside and we've got this non-uniform load, this is going to be better at resisting that load because now it's more towards one side of this floor than the other, compared to something like this where we've got the braced frames on the inside. Okay, so if we were to treat this as our simply supported beam like this, we've got some load here. And of course, the load over here is going to be slightly bigger now than the one on the left. But if we compare that to this system, where we've got a pin and a roller and a beam with this uniformly distributed load on it, this one's going to be much bigger than this one. Right? So from a structural design perspective, keeping the braced frames on the outside of the building will reduce the amount of load you have to design them for when we come to non-uniform loading. Okay, putting them closer to the face of the structure means they have to resist a bit more twist, and that's going to mean that there's going to be more load on those braced frame members, which means you need to make them bigger. From an economics perspective, we want to keep things small as possible. Also, a less ideal case, maybe the architect's like, okay, you can put your braces there, there, and there, but I want this face to be glass, and I don't want any braces in my glass. In that case, even a uniform load is going to result in more load on that braced frame system. Now we've got something that looks like this. So even if it's a uniform load, statics tells us we're still going to have a bigger force on that braced frame than on the other. And so that means we're going to need to design this to be a little bit heavier. And it also means the floor might twist a little bit. And we're not going to talk about that too much in this course. But these are some things to consider when we're talking about braced frames. Now, we've got not a lot of time, but I'll at least try and put some of these concepts together for us. We've got an example here where we want to calculate the lateral load acting on the braced frame at column line 1. That's this one. At floor 3, if the height above and below the stories is 4 meters. And we're going to take uniform pressure of 0.94 kPa. I'll show you where that comes from later on in the course. But basically what we're going to do is we're going to say this is 0.94 kPa. This height here is 4 meters. This height here is 4 meters. And what that means is if we think about this as a tributary width, what we're trying to calculate ultimately is this load here, this point load at floor 3. So we need to figure out what the uniform load is on the floor system that's coming in from the wall. The width of our building is 42 meters. And that comes from the floor plan here in the example. We've got 4 bays at 10.5 meters, which means it's 42 meters. And basically the pressure is coming from the south face, something like this. Okay, so we want the uniformly distributed load acting on that floor from a pressure of 0.94 kPa acting here. And so if we were to draw that floor system, maybe something like this, we would say that the tributary height or width for that strip is 4 meters plus 4 meters over 2, which is 4 meters. And if we want to calculate W, the uniformly distributed load on the floor, that's going to be the pressure times the tributary width for that height. That's 0.94 kPa times 4 meters, which should be something. That's not a unit I like. That gives me 3.76 kilonewtons per meter. So I know that the floor is seeing just under 4 kilonewtons per meter from this pressure acting along the width of the floor level. And what I want to do is treat this as a simply supported beam where I've got a pin and a roller at the location of my braced frames. And what I want is the reaction at the left-hand side, because that's going to be the action on the braced frame at this level. We've already gone through statics problems like this. This is a pretty simple one. We've got a uniformly distributed load. We want the reaction force over here. Let's say this is RB, this is RA. RA is WL over 2. We talked about that again in lab the other day, 3.76 kilonewtons per meter times 42 meters over 2. That gives us, we'll call it 79 kilonewtons. Okay, so we've got a pressure pushing on the floor. We figured out how much it's pushing on the floor as a force per unit meter of the floor. Reaction is simple for the statics problem. It's just half the load divided by 2 because it's symmetrically loaded in this case. If it was non-uniform, you'd have to do something a little bit different. But the problem here is not just to calculate that load, but it's also to draw it on a free body diagram of that braced frame. This is our braced frame system. We're going to idealize this as a truss with all the same members, but with joints that are frictionless. So we're going to draw it something like this. I'm going to put a pin here, going to put a pin here. And that load at that location is 79 kilonewtons. Okay, we would of course want to do the same thing at this level, and at the roof. And in fact, the pressure or the force at this level, because the tributary width and the pressures are all the same, that should also be 79 kilonewtons. At the roof, the tributary height of the roof level is going to be half because there's no floor above it. So it's just going to be half of the force we calculated, which is going to be something like 39.5 kilonewtons. And then the force at the bottom, I should have given myself a bit more space here, but that's going to be just a little bit bigger because at the bottom of our structure, we can go to the elevation view. Here we've got 4.5 meters. Here we have 4 meters. And so our tributary width there is going to be 4.5 plus 4 over 2, which is 4.25. So the load at the bottom might be 5% higher. We'll say that's maybe 83 kilonewtons or something like that. Okay, so all of a sudden we're at a point where we can figure out, if we idealize our brace frame system as an ideal truss and calculate the loads acting on these locations from the pressure coming in from the wall system, we can now go back to first year statics and figure out what these frame member forces might be. And the purpose of figuring out those frame member forces is to figure out how big those braces need to be so that they're sufficiently strong to prevent them from failing under that applied load. Okay, any questions about that example or process before we wrap things up for the morning?
Can you go back to the other slide?
Good? Okay. So now you should be able to identify brace frames and braced frames and how they're arranged to carry these lateral loads. Should be able to calculate the forces acting on the brace frames. We just went through an example of that, and draw the lateral forces on a free body diagram of that truss representing the brace frame. We just did an example of that. And you should be able to differentiate between statically determinate and indeterminate bracing, as well as tension only or tension compression bracing. Before you wrap up, is this tension compression bracing or is this tension only bracing, do you think? Who said both? Can it be both tension only and tension compression? I've kind of made it a little bit weird here because there's one brace, but if wind pushes the building this way, we've already known this is going to be in tension, but if the wind's coming the other way, it's going to be in compression. It has to be designed for a tension force and a compression force. We cannot make it tension only, because if the wind pushed the other way,